So here's a model. This is the notion for what a new solar system would look like. It looks like an egg on a plate, right? Now this is the new star, right? Okay, there's the little star, right? Okay, there's rocky stuff, right? And why is there going to be icy, gassy stuff far from the star and rocky stuff close? Why would that be? Not necessarily density. Why couldn't there be ice right up close to a new hot star? It's too hot, right? So it's going to, any ice that was here is going to evaporate and deposit itself on the accretion disk farther away, right? That's the idea, right? Now, why are we saying this? What's the only example of a solar system that we've really observed? Our own, yeah, what do we got, right? Okay, if we look at our own, don't we have rocky stuff close to the sun, icy and gassy stuff far away, right? So this is, there we go, right? Not a lot of wonder there, right? So the inner planets are all made of rock, and the outer ones are gas, right? There's no surface. In other words, these gas giants don't have a surface. You can't stand on them. It's just gravity, right? Yeah, just gravity sort of holds them in a blob. Like in the space station, if you were to shoot a blob of water into the air, it would form a sphere, not because of its own gravity, because of something called surface tension, right? But it's the same idea. It's just a uniform force like that. My wife had that same question. She was like, "Well, if they're really a fluid, what makes them, hold their shape?" So presumably, if a couple of these collided, they'd be like water globules in the air. They'd sort of undulate or something like that, right? These are pillars right here. These are giant pillars. There's these things themselves are pillars, and then on the pillars there are pillars. Those pillars are just knots of material that have already collapsed, and they're dense, so they're protecting. Again, there's a supergiant star way above this that's blasting this away. That's why it looks like a waterfall. And then these are little knots of material that are protecting it. Sort of like if you've got little chips of bark on top of dirt, after the rain, aren't those little chips of bark sitting on top of pillars of dirt? Because the dirt around it's been washed away. Have you ever noticed that? I noticed stuff like that. I don't know. I don't know. I think that's what's going on, right? Here's, again, these are the two colliding galaxies. These new stars are getting born because when the galaxies collide, it causes these clouds to collapse, right? And then spiral galaxies make stars in an ongoing process because the inside spins faster than the outside. So it's like one of those, washing machine, right? An agitator, right? If the inside's spinning at a different rate than the outside, then it's always churning and churning and mixing and mixing. And when it does that, it causes these things to collapse. And so spiral galaxies create galaxies at a certain rate, 1,000 a day or something like that, right? They create not galaxies, they create stars, right? 1,000 a day or something like that. So galaxies are full of old stars and new stars. It's creating them in an ongoing process like that. Okay. And then this is just the center of our own galaxy. We've got something going on that's creating these are giant new stars. We know they're new because they don't live very long. They have to be new, right? Again, this is just clouds of stuff. There's stars being born there. I thought that was a good thing to have a lot of pictures of. Apparently a lot of pictures, right? Here's, these rings here are from a supernova, so that's the spectacular death of a supergiant star. Here's one of those pillars, and I think we've seen a close-up of that pillar, I believe. Might be the one with the jets on it, right? Okay, again, this is a nebula in that galaxy, right? Another nebula where stars are being born. Look at all the stuff. You can see the background of stars. This is just leftover stuff, debris from star explosions, etc., right? Okay, now once you've collapsed, now you're on the main sequence. And when you're on the main sequence, basically your job is to turn hydrogen to helium. And this is the biggest bang for the buck. The most energy that you can get is from turning hydrogen to helium, and there's really not much. You can go helium to carbon like things, carbon to things like iron, but none of those are quite as good as this, right? So stars spend most of their time on the main sequence because there's not much to be had after that, right? Okay, and this is in your notes, isn't it? Yeah? Yeah. Matt! Hey, Matt! Oh, school time. It's time to go to physics class. Okay, now, this is a key concept here, is that there's two forces acting in a star, right? One is crushing a star, right? The other is plumping the star up, yeah? And so, Matt, think fast. Oh, he didn't think too fast. Let's try again. Think fast. Oh, you got to catch it. You got to wake yourself up. All right. There's two things going on, right? There's gravity. Gravity is crushing the star, right? And the other thing that's going on is there's a nuclear explosion in its core, and the nuclear explosion in its core is plumping it up, right? So if I hit the arrows, we get, of course, these nice things, right? So there's heat, there's thermal agitation. Basically, there's also explosion, right? It's like boom, right? Now, this is a stable equilibrium. Here's why. Let's suppose we were like God or something like that, and we crush this. We just go, right? Well, what's going to happen if you crush the star? What happens to the pressure and the heat inside there? It gets bigger. What happens to the rate of nuclear reaction? It gets bigger, and so the force pushing out gets bigger as well. So it's not like these things are unstable. If you started to crush one, it would immediately resist you crushing it by exploding harder and harder, right? The harder you press, the harder it would push back. Does that make sense? If you took a star and somehow expanded it, well, then the nuclear reaction would slow down. Gravity would pull it back, right? So these stars sit there on the main sequence, and that's why there's this pattern, right? If you go bright, isn't this bright and dim and hot and cold? No, it's the other way, isn't it? No, it is. It's this way, right? Okay. That's why they look like this. It goes, no, right? Because super hot stars, they all fall on a certain thing. There's a certain size, a certain temperature, a certain equilibrium point that they all fall on, and it just depends on their size. The size is the parameter, right? Right. So this is small. These guys are big, right? Okay. And then this is the death knell, right? Where's the helium going to go? Helium is more dense. A helium nucleus is more dense than a hydrogen nucleus. So where's it going to go? Right to the middle, right? I hate that, right? It's like eating a hot pocket, right? Where does it go? Right into the middle of your gut, and then it just stays there, right? This one gets bigger and bigger, right? Yeah? Okay. So here's the crazy thing, is that the helium is starting to fill up this space. Now, we're not hot enough to fuse helium yet. So this is a recurring thing. This happens a couple other times, right? This is another key concept, is that the reaction now, if it's not happening in here, because it can't, that's all helium, and we're not hot enough to fuse helium, where does it have to happen? Where does your reaction have to happen? Outside of the helium core, yes? In fact, it's all happening right on that outside of it. Now, as the helium core gets bigger and bigger, that's bad news if you're doing hydrogen fusion. Why? What's happening to the pressure and the heat as you go out in a star? It's getting less, right? Pressure and heat gets less. The core of the star is the hottest. Everything else on the outside, right? It gets cooler and cooler as you go out, right? So if the fusion is happening right here, and you're always pushing it out, right? What is happening to what's eventually going to happen to your hydrogen fusion reaction? It's going to stop. Now, that's bad news for a star, right? You can stop exploding, but gravity never quits crushing. You can stop exploding. You can run out of fuel. There's lots of reasons why you stop the explosion, but gravity always crushes. Okay? So what happens then, okay, is that this thing, as soon as it cools down, gravity goes, gotcha, and takes the star and just goes and crushes it. Okay? Now, this is, by the way, how we make hydrogen bombs. Hydrogen bomb, we take a uranium or plutonium device, and we take lithium hydride, and we just basically slam it with a shock wave, right? Lithium hydride is a solid substance that is most hydrogen by mass than any other substance, correct? LiH4, right? Okay. So what you do is you slam that with a shock wave. Well, here we've just got hydrogen. We don't need lithium hydride, right? When gravity crushes that helium core and it's just going to go boom like this, right? All of that hydrogen suddenly slams into the other hydrogen. What's it going to do? It's going to go kaboom, right? Right? So as that crushes, and I don't know how long that takes, it's not like a kaboom, like instantly, right? But as far as astronomical time, as far as millions of years, right? I think it's like thousands of years, right? It puffs up and it becomes a red giant, right? So that's what's going on here. Da-da-da-da, right? But meanwhile, back at the ranch, right, we're about to become